Hello and welcome to my first stream. I'm going to spend today talking about how to design your own PCBs. If there's anyone out there listening, that's great. I'm doing this as a stream to give people the opportunity to ask questions that might come up through this process. But if not, this will be recorded for posterity so people can review it later. I'm going to go through using KiCad as the platform to design the PCBs, and I'm choosing it for a few reasons. One, it's an open source software, so it's free to use. I recommend, if you want to follow along, go to KiCad.org and download it and get it installed. It's a very, even though it's an open source software, it's a very powerful software. There's certainly paid programs out there for doing PCB design. Altium's a really popular one, but they can cost thousands of dollars for an annual license. Hello, I see you in the chat. Can you hear me fine? But KiCad, despite being open source, is a very powerful piece of software. My day job, I work for a company that builds space robots, and we use KiCad for all of our PCB design. So, it's good enough for use in cutting edge space technology. It's certainly good enough for your hobby project. I think it's the learning curve for KiCad is, not the easiest. Any sufficiently advanced CAD software is going to have a bit of a learning curve to it, but it's not too bad. And there's still some quirks with it that trip me up every once in a while. I am not an electrical engineer. I am an engineer, but not an electrical engineer. I'm more of a hobbyist on the electronics side. But I've designed and through production, a half dozen PCBs, if not more at this point, using KiCad. So yeah, it's excellent. Thanks for confirmation that you can hear me. So yeah, let's get into it. Before I get into using the KiCad software, there's certainly a lot of basic understanding of schematics and electronics that you kind of need to know in order to know what you're doing. So I'm not going to get too deep into that, but I do want to cover it a bit. I've put a link to the SparkFun tutorial in the description here, and it's just kind of an overview of different symbols. So I'm sure you've seen electrical schematics before. Hopefully you've seen electrical schematics before. And there's certain symbols that represent different things. So resistors, depending on, whether you're European or US, you may see it as a squiggly line like this, or a simple rectangle with two leads coming off of it to define the pins of the resistor. Variable resistors are the same thing, but with an arrow through it or pointing towards it. Switches are usually like these segments of lines with like what is displayed as a physical switch between them to turn it on and off or switch between two things. Capacitors are usually these parallel lines. Like when you see two parallel lines like this, that's usually a non-polarized capacitor, and then you have a polarized capacitor with one bent line and usually a little plus to indicate the positive side. And you have inductors and diodes or LEDs. These BJTs here are transistors, and then you have logic gates, and then down here you have chips, right? So logic chips, or maybe it's a ROM or RAM or something like that, and usually it's just a big rectangle with a bunch of leads, and then those pins or those leads represent pins that are labeled. There's certainly more symbols than this, but getting a little familiar with this and knowing what the different symbols mean, keeping a reference like this handy, so if you're looking at a schematic, you can know what it is. will help. So yeah, having a basic understanding of electronics and how to read schematics is definitely going to help you out when you get into KiCad. So this is the KiCad application, and I have a project open right now. This is the main screen. KiCad's made up of a bunch of different tools. The two tools you're going to use the most are the schematic editor and the PCB editor. That's where most of your time's going to be, and the rest of this are kind of like tools that you use depending on the need. But pretty much every PCB you're going to be designing, you're going to be using the schematic editor and the PCB editor. And then over here, this is just when you create a project, it creates a folder, and it's just going to dump all your files in that folder. So over here, this is a folder for a multi-kit that I had designed. For those of you who aren't arcade enthusiasts, multi-kits are kind of like a PCB that sits on top of an arcade PCB to allow you to switch games. So let me open this up and just kind of show you what an example of one of my schematics looks like. So the schematic editor, this is what the schematic for that multi-kit looked like. So you can see it's basically just got a bunch of chips. Well, actually, some of these, this is a header, so this plugs into the board below it. This is a chip for a programmable logic device. And I have some sockets here or chips here for ROMs. I have a rotary switch here that's what you use to select the game. That's tied into a few different resistors. This is just like a header for connecting to an external device. This here is an oscillator, so it's like a 30 megahertz oscillator. And then down here you see a bunch of capacitors, and these are to help keep the voltages stable throughout the board. So you might notice that you think of a schematic, you think of like lines like these going everywhere, but the way I've done this is it uses references. So the idea is that when you say something like 68K A23, you see this little flag here, it actually you can imagine a line going between these two, and I can use this same reference multiple places. So you have one here, one here, one here, and those are all sort of virtually tied together, and it makes it a lot easier to read the schematic, and it keeps it a lot cleaner. I can tie something here all the way over to the other end of the board, and it's not going to make it super messy. And then I do actually draw lines for like smaller stuff just like this, where it's kind of just localized. But I'll get into that in more detail. So that's a schematic editor. Usually the first step in doing a PCB design is drawing the schematic, understanding all the electrical connections there, not necessarily how it's physically laid out. So then the PCB editor is that physical layout. So this is the PCB. So this is the PCB, and this is, the physical dimensions of the board, and then you see the actual pins of the chip, and then the traces that connect all the pins together. You can see in some areas it's pretty simple. You have just lines going up. In other areas it can get really complicated. All these little dots are vias, and a via is something that like passes the trace from one layer of the board to another. So yeah, this is kind of the two things here. And once you've got this, there's some cool tools, like there's a button up here so you can actually generate like with a single click of the button. Wait for this to load. It'll create a 3D model of your PCB so you can kind of see how it will lay out. Really neat tool. You can even export these to use to design your enclosure with like a 3D printer or something like that if you wanted to. There's also like a button here called the fabrication toolkit. This is a plugin that I've installed, and this allows me to create all of the files necessary to send this to a fabrication shop to get this manufactured, including, you know, placement of all the components and things like that. So that's kind of just like a high-level overview of this. Yeah, I don't need to save that. Some other things here, you have the symbol editor, and what this does is this is a tool to create new symbols for your schematic. So like, you know, I showed you that diagram and it had some chips in it. So this, you know, this right here is an ATF 150 1502AS. This is a programmable logic device that I used in a few of my multis now, and I didn't have a symbol for this to use in my schematic, so I drew this using this tool right here. So we have there's lots and lots and lots of stuff in here in the default libraries with KiCad. Really great references. You can see even some regular products, like we have these FPGAs, Xilinx FPGAs, and even simple stuff like relay. So yeah, you know, that's a relay. There's a different relay. Let's see what else is in here. Touch sensor, temperature sensor, transformer, transistors. So yeah, there's lots and lots of stuff in here. And when I need to design a symbol that's not in here for a device that I want to use, I'll typically find something similar and I'll make a copy of it, and then I'll modify it to my needs. So you can see here, these are starred. These starred ones are, you can star them to filter it to the top, but most of these that are starred, in fact I think all of them that are starred, are actually my own libraries that I've created with devices that I use frequently. Some of these, like ROMs, like, you know, if I'm doing arcade stuff using EEPROMs a lot, I think there was a few of these in like the standard libraries, but I kind of copied those and then tweaked some additional ones to my liking, so that they're all kind of the same. Resistor networks is some that I've created. This is a RAM. I don't think this particular model of RAM was in the library, so I grabbed a similar model and then tweaked it to my needs. And then the footprint editor is very similar to the symbol editor, except this is for creating custom footprints that are used on the PCB side. So you have the schematic symbol, and then you have the footprint of like how it's laid out physically on the board. And they're separate things, because you may have like 5 or 6 different devices in your schematic that all use the same footprint. Or similarly, you may have a single device. So like here's a good example. You have a capacitors, right? Or yeah, you could have a capacitor, and like the footprint for a capacitor, well, these are surface mount capacitors. Here's the through-hole capacitors. So you have a capacitor, right? And the footprint's just 2 pins. But that same footprint could technically be used for a resistor or any other 2-pin device, as long as those pins are the same distance apart. Let's see, connectors. So like there's generic connectors in here. So there's a 1x3 or 1x, that's a surface mount. 5-pin connector. So there's maybe, you know, this same footprint that's 5 pins could be used for dozens of different actual connectors. So yeah, that's kind of why they're separate. But there's ways to tie them together in your design. I'll show you how to do that. And then some of these other ones, like Gerber Viewer, this is sort of like opening the production files. I don't think I've ever even used that tool. this image converter. So if you want some like cool things printed on, cool symbols or pictures printed on your PCB, this will convert images into the symbols that you can use. Calculator tools and drawing sheet editor. I don't think I've ever really used these too much. And then there's a plugin, content manager. So there's lots of plugins for KiCad. This is kind of a way to search through what's available. There's lots and lots and lots of stuff. On mine here, I have this free routing plugin. I think I installed this, but I don't really use it. 3D Model one to sync your design with Git. Fabrication Toolkit. This is the one I use most frequently to output all the files I need to get it produced. I'm seeing in the chat someone mentioning sites like DigiKey and Mouser have downloadable parts. Thanks Mitsu. There's a website called certainly. Part sites like DigiKey and Mouser will have footprints that you can download, as well as maybe some schematics or schematic symbols. There's also a website called Ultra Librarian that I've used, and then there's a few paid sites that offer it too. I've used them on occasion, but to be honest, I found I prefer to just draw it myself. A lot of times when I've had something I search for a footprint on, and I've ended up just getting frustrated with the way whoever drew it, and just redoing it myself anyway. It doesn't really take too long to do it yourself, and if it's something that you're going to use more than once, it's probably worth doing and keeping in your library. So I'm gonna walk through and recreate from scratch a design that I had done before. So let's close this project, and we're gonna do a new project. And so I'm gonna create a folder, and we'll just say resistor module example. So there's a Toplin shoot 'em up that used a custom resistor module for the inputs, and I recently drew up a schematic for this. So I just created a folder. I'm creating a file the same name, and you can see it created schematics and PCB for me. So we'll open the schematic editor, and we're greeted with this blank page. You'll see here on the right, it's got these lines around the perimeter and like this block down here. This is a typical engineering layout. So when you see like professional engineering drawings, this will have this kind of border and block down here. You can customize this. I think that one of the tools, this drawing sheet editor, is how you customize that. I, to be honest, just ignore it. I don't use it for my own projects. I guess if I was gonna print this out and hand it to a professional fab shop or distribute it to other engineering teams, it might be useful. But one thing to keep in mind is that this by default is A4 size. You can see that listed down here. So that's a standard 8.5 by 11 sheet of paper. If you go up here to File, Page Settings, you can change the size. This is also how you change the drawing sheet template you're using. You can also change portrait or landscape. So if I'm doing a larger design, I'll bump this up to like an A3, which is a much larger sheet, and that gives me more room to play with. For this though, this is a really small board, so we're going to stick with the A4. And I'm using like the scroll wheel on my mouse to zoom in and out. There's lots and lots of keyboard shortcuts that are super useful in KiCad. So I'll try to remember to explain those as I use them. So started with this blank page. First thing we want to do is we want to put some symbols on here. Well, actually, let's talk about what we're actually going to design. Let's see. So this right here is the device that we're trying to duplicate. This is called a resistor network, and what it is you see this row of pins here, and there's a bunch of resistors behind this black sheeting that connect these pins together in different ways. And the idea is that they need this circuit produced like dozens of times on this board, so they make it into a module that they can easily install. As you can see here, there's 4 of them. There's probably even more on the actual board, and that makes it easier for them to produce this, and it makes it easier for them to like take this design and use it on multiple boards. But the problem is, because this is like a special design made by Toplin, it's not a part that you can just like go to DigiKey and buy. So if it fails, you're kind of screwed unless you want to produce a replica of it. So that's what we're going to do today. Now, someone, I don't know who made this, but someone was kind enough to poke around or maybe disassemble one of those modules and work out what the inner layout is. So if you see here, we have some 4.5 kilo ohm resistors. So the assumption is that this row here are 4.5 kilo ohms. Then we have 250 ohm resistors, and the assumption is that these resistors here are 250. And then a 1.5 kilo ohm over here. And you see pin 1 is connected to 5 volt, pin 14 is connected to ground, and then pins 2 through 13 are for different inputs. So this is a schematic that someone made. So we're going to essentially duplicate this so that we can produce it. Yeah. So let's so what I'm going to do here is I'm going to click this button over here. So this is the symbol button. So now it opens up this selector so I can find my symbols, and you can type in the top here, just quickly search down. So I'm going to type in resistor. So you can see there's some resistor networks in here already. Actually, I think both of these are ones that I made already. We can minimize that. We don't need sensors. It's not a potentiometer. So what do we got? Where are my resistors? Wonder if it's under some weird name. Maybe not. It separates the capitals and the lowercase. That's what it is. Or not. I am not sure why I am not seeing my resistor list. Oh, interesting. So under device, it had resistors. So, a few different symbol options here. sometimes this will matter, sometimes it won't. I'm going to go with this small US symbol for no particular reason. So, place a component. Very simple circuit. So what I'm going to do now is I'm double clicking on it, and it's going to open up the properties. You can see R1, the value here. So if we look at this here, let's make this a 4.5 kilo ohm. Oops. So a way to write that is 4K5. And now in this same sheet here, we can determine our footprint. So when I click that, it's going to open my footprint selector. So let's see. If I wanted to, I could make this a through-hole resistor, and that would make it really easy to solder. So we have a resistors surface mount, and resistors through-hole. So I have a whole bunch of different through-hole resistor footprints I could use. But I want to keep this really, really small, so I'm going to go with a surface mount option. And you can see there's a whole bunch of different options here too. So which one should you go with? Well, let's look at, so if you there's different sizes here. I just had this already pulled up to use as a guide here. So you can see there's different sized physical resistors you can use, or through-hole resistors you can use. And for surface mount, these are like the different sizes here. So you can see this 402 is tiny, tiny, tiny. The little black dot there is the resistor size. And then you have like, this 1608 here is much larger, and then they keep getting bigger. For me, I like this Imperial 402 or metric 1005 or this 1608 0603. Those to me are like the sweet spot where it's small, but it's not so small that you can't actually solder the thing by hand. Another thing you could do is start looking at what parts are available. So I use JLC PCB to make my boards, and they actually sell parts just like Mouser or DigiKey. So if you go to JLC PCB/parts, I could search for resistors, right? Let's say I want to .0603 package. R0603 is kind of the same as 603. They're just identifying that it's for a resistor. Capacitors also have similar sizing. So you can see I have all these different options here for resistors, and I get the price here. And the nice thing about with JLC PCB and using their part shop is if you're going to have them fabricate the boards, you can have them pull the parts from their own inventory to place them on the board for you, which makes things super simple. Here we go. So what size was this? This was a 4K5. So the resistance 4K5 is a bit of a weird 4.5K. It's kind of a weird size, not a real standard size resistor. So we might have to pick something close. Yeah, so they have a 4.48, a 4.53, 4.59. Resistors, this isn't like a precision voltage regulation application or anything like that, so we can just pick some close ones. And you can see there's like over 3,000 that meet that criteria. So and where's my package size? So we wanted a 603, right? So there's 316 options. And you can see what they have in stock here. So I'm going to avoid these that have like 8 in stock because I'll probably deplete their stock pretty quick. Let's sort by. So there's lots in here that they don't have in stock. So let's check this box. So there's only 22 that in stock that meet our criteria. And so this chip here, they have 35,000 in stock. It's a penny. So this is a really great one to use. So they have it in 603. It's not exactly, it's like a fraction off on our resistance. Negative 55 to 155 degrees Celsius operating range. So I think this is a pretty good option here. Now, one thing I will do here is you'll see this JLC PCB part number. So I'm going to grab that. So we decided we wanted the 603 footprint. And if you notice here, this, oh wait, yeah. There's a couple options here. You have the regular 603 footprint, and then you have the hand solder variant of it. And the difference here is the hand solder one has slightly larger pads. So I'm gonna pick that one. So now my footprint's been selected, and I'm gonna add a field. I'm gonna say JLC PCB part number. I'm gonna drop in that part number I copied from the page. Now, I did all that up front because we have 1, 2, 3, 4, 5, 6 of those resistors. So we're gonna, now that we have all that set up, I'm gonna push the R key. It's a shortcut to rotate, and I'm going to Control C and Control V. 2, 3, 4, 5, 6. Man, these are right on top of each other. I can push the. I can either. So if I, now that I'm dragging it, let's. You know what? I'm gonna space these out a bit. So I'm just clicking and dragging to space them out. All right. So that's that list of 6. So now let's look at these 250 ohm. So I'll copy one of these and I'll paste it, and I'm going to modify it. Again, double clicking on it to open the properties. And this is 250. We want the same 603 footprint. For now, I'm going to delete that JLC PCB part number because that's no longer correct. And let's go back. Let's go back here. So we're going to clear the resistance, and we want 250 ohm. Oh, that's 250 mega ohm. Don't want that much. Come on. 250. Why are they tell mega ohm? I'm sorry, those were milliohm. That's why they came up before. 250. It's 13 options. So let's look here. This looks like a good one. Again, only a penny. So I'm going to grab the JLC PCB part number and we'll paste that here. And for this, we again have 1, 2, 3, 4, 5, 6 of them. 2, 3, 4, 5, and 6. So you'll notice that like KiCad's automatically adding these R numbers for me. So every device on your board should have a unique number. Different types of devices will have different prefixes. So R is what's normally used for a resistor. C is normally used for capacitor. You can see here U is a really common thing to use for a chip or an integrated circuit. X is commonly used for oscillators or crystals. J is a really common one for connectors. Now, in the symbol itself, the prefix that they use is already determined. So if I open up my symbol editor or symbol selector, you can see R is already added there for resistors. These devices here already have the U identified, so that as soon as you place it, it's going to automatically assign it a number after there. You can customize these if you want. So if I really wanted to, I could change that R to anything I want. But I think it's probably best practice just to leave it with the common nomenclature. I will also say that KiCad really does not like if you end it in a letter. So if I said R1B, it'll accept that, but there's tools down the road and things that it's going to cause problems for you if you add a letter suffix. So the rules kind of are, it should be unique and it should end in a number. And if you follow those rules, you'll be in good shape. Alright, so we have this row of resistors and this row of resistors. We still have this 1.5K, so let's do that. Grab that resistor, drop it down here. You can see it automatically did the next R number, so it's R13. Oops, double click on the symbol itself. So that's 1K5 for a value. And again, we're going to delete this JLC PCB part number for now. Come back here. And let's find lost my search. So that is a 1.5K, and the package type again is 603. And select both of them, and we're only looking for in-stock stuff. There's a lot more options here. This is clearly a much more popular resistor. Again, I think this first option's a good one. I'll grab the JLC PCB part number, and we'll drop it in here. Okay, so now we have all of our resistors, but there's one more part that we need, and that's the actual connector to connect this module to the donor PCB. So we'll go back to our symbol selector and we'll look for a connector. So I think connector generic, and this is a 14 pin connector, so we want a 1 by 14, because if you remember, it's one row, 14 pins. So that's this one right here. So I could place that here, but maybe I could again rotate this if I wanted to. But if you notice, now that I've rotated, the pin 1's on the bottom. So let's see what I can do with this. I think I can flip it. Oops. If I right click on it, oh, I know. Up here, here's my flip. So I'm going to rotate it back to its original position with 1 on the top, but the connection's on the left hand side, and flip horizontally. And there we go. So you can see this is automatically labeled at J1 because it's the first connector I've placed here. I can rename the value as kind of its description. I can say con1 or whatever I want to call it. So now I can actually start drawing my lines to connect these components together. So if we look here, pin 1 goes to 5 volt and pin 14 goes to ground, and then pin 2 goes to your 4.5K. So if you see here on this right hand side, this there's a button here for draw wires. Don't get it confused with the draw buses. That's a totally different thing. So this thinner line, draw wires, it's going to go from pin 2. So this is one of the quirks here. You can see that like the line's not necessarily going where I want it to go. So you can click mid-draw to kind of lock in what it's drawn so far. So let's click there, and then I can go up and over to connect there. And then this here goes to there, and this here. So it goes to 3, but I don't want it to overlap like that, so I'll click here, and then draw it to 3. So you can see now I've made like this pin 2 to this resistor and pin 3 to this resistor, and then these two resistors together. And this back line here are all connected together. So that's a really easy one. I can just do this. You can see it's automatically, because it overlapped, it automatically connected them. And now let's keep on drawing these. Not the cleanest, but it gets the job done. So now we have this 1.5K. So this row here goes straight to pin 1. So we can do that. And that back row also goes to one end of this 1.5K. So we'll do that. And the other end of that goes to pin 14. Now if I wanted to, like, so here's another one of those quirks. Like, this looks a little messy, so let's say I wanted to rotate this. Well, now it's broken my wires. So you kind of, when you do those kinds of things, you kind of just need to select and delete and then redraw. I'm just pushing the delete key on my keyboard to delete those after I highlight them. The escape key, so notice I have wire selected. If I push escape, it goes back to the default selector tool. So delete key, reselect that, and now I'm going to redraw this. So that's kind of all of it. It's you can see it's the same circuit, but it's just described a bit differently. So now that I've done that, oh, you know, one thing we didn't do is we didn't select our footprint for this connector. So we forgot our footprint here. I don't consider the schematic complete until I've kind of set the footprints for every one of my components. Well, you know what we'll do? We'll not select this so I can show you what happens when you forget it. So before we exit out of our schematic editor here, let's save it. And there's this button up here for Electrical Rules Checker. So I'm going to click that and run it. And what this will do is this will go over our schematic and just let you know if it sees anything problematic. So let's say, like I forgot to connect this here, right? And I run the ERC. It's going to throw up some errors here. Say, hey, you know, this thing's not connected, this thing's not connected. And then it calls out, you see these little arrows here pointing out the problems. So then we can fix it. And we can run the ERC again. And it came back with no errors. You can do things like there's some defaults I have here to ignore. So sometimes you'll be doing something and it's like, yeah, I know it's like that. I want it to be like that. So just ignore that error. Yeah, so it's a really useful tool to kind of like sanity check. Hey, it's not going to make sure your schematic is what you intended it to be, but it will make sure that you don't have any goofs on it. So now that we've done that, let's move to our PCB layout. Now, there's a button right up here, so instead of having to like exit out of this screen, back into this screen, and then select the PCB editor, we can just click here and it will automatically jump us over to the PCB editor. So again, on the PCB editor, we have the same kind of layout thing I mentioned before, and the same way if you wanted to, you can go to the board setup, not board setup, page settings, to select a larger size or change it to portrait if you wanted to. Now you'll notice this is a blank page, so how do we start here? Well, there's this nice button up here. You can see it's like half and half schematic PCB, and what this will do is this will import all of your schematics into the PCB editor. So I click that. Now we see we have an error, and the reason we have an error here is because we didn't assign the footprint to that connector. So it's like, hey, you know, I see that you have this component here, but there's no way for me to place it on the PCB layout because I don't know what size it is and I don't know what the holes are. So because that failed due to error, we're gonna, you know, like I could, if I really wanted to, I could click this update PCB and it will pull in all the stuff minus that footprint. But I'm going to say, oh, you know, let's go back to our schematic. Again, there's like a handy button up here to switch back to the schematic editor. And now we can go and set the footprint for this connector. So one thing, if you look at these. This row of pins here, like most through-hole stuff, especially on arcade boards, is a really standard footprint spacing of 0.1 inch or 2.54 millimeters. So 2.54 millimeter header means that every one of these pins is 2.54 millimeters apart. So you can go to connector, as you see connector, pin header, 2.54 millimeter. So, and this is, it knows automatically, because it's doing this, maybe, yeah. So this little checkbox here is applying a filter, and it says that, you know, my device is 14 pins, so I'm going to limit it to 14 pin things for footprints. And we see the different options we have here. So this is a vertical header, and this is a horizontal header. You can see the horizontal has additional spacing allocated for the pins. So we're going to select the horizontal header. And again, I can add JLC PCB part number if I wanted to. Let's see if we can find one. So connectors, pin headers, and we're going to find number of rows is 1. It's a single row. We have 14 pins, and we want through hole right angle. So I think this right angle here is through hole, even though it doesn't say it. I don't really care about length right now. The pitch, 2.54 millimeter. And we want to make sure it's in stock. So there's only 9 results left. And let's sort this one by price. So here's a 3-cent part. It's 400. No picture, which is not great, but you can see even on JLC they have. Sometimes they have footprints available, but they did not on this one. So we'll copy this part number and we'll paste it here. And we'll save it. And now we'll go over to our PCB editor and we'll do the import again. No errors this time. Great. So click Update PCB. Now, if you want, like, let's say you do this and then you decide, oh, I need to change something on the schematic. You can go back, check on the schematic, and then run this again. And some of these checkboxes here will allow you to do different things like overwrite or duplicate or whatever it is you want to do. Okay, so you see it kind of pulls in all of my components as a group. So trying to make sense of this, if you see this like yellow color here, that's silkscreen. This red color here is top layer copper traces on the PCB, and this pink border is kind of your keep out zone. So it's like, hey, you know, make sure you don't place any other components within that pink border. And you can see on the surface mount stuff it's even tighter. And if you zoom in further, you see we have the pad here, this kind of squared, rounded square, and then you have this thin line around the perimeter. And that thin line is basically saying, even though that's not part of the pad, you want to make sure you don't have anything else overlapping there, any other electrical connections overlapping in that area. And that's just to prevent shorts from happening during production. Then you have this gray color here, and that's kind of just for reference in this document that won't actually show up on the PCB when you make it. And all of these color references are kind of listed on the right hand side here. So most PCBs, realistically, a PCB is just a bunch of wires in a really compact form factor. So anything you can do with a PCB, you could do just hooking wires together on these different components. It'd be really messy if you did it with wires, but think about a PCB in that way. And the simplest of PCBs are one or two-sided. So if you think of a PCB like a flat plane, you could have electrical traces on one side or electrical traces on the other side. So if it's only on one side, that's a single layer. If it's on both sides, that's a two-layer. You'll have holes that go through the board that connect the two layers together at a certain point, and those are called vias, and that's how you connect one side to the other side of that board. But more complex boards could have 4 layers or 6 layers or 12 layers. So if something like an arcade board or a lot of the hobby projects, like I don't do anything more than 2 layers. But if you were to look at a PCB for, like, say, a smartphone or a laptop or even the motherboard of your desktop computer, those are going to be 4, 6, or 8 layer PCBs. So they're able to have much higher density of traces going through everything. So some of the stuff here is similar to the other one. So like I can click and drag. If I push the R key, it rotates. One thing that's unique here is you notice that I mentioned these are all showing kind of top layer, or as this is identifying front layer and back layer. If I push the F key, that flips it, and that's making the assumption that this is now mounted to the back of the PCB as opposed to the front of the PCB. So I flip it again, bring it back, and this is probably more apparent on the surface mount resistors. So these pads are all red because that's identifying the front layer copper. But if I push F, you can see it flipped the symbol and it turned it blue, and that's telling me that this is on the back layer copper now. And the reason you see the logo flipped is because now it's on the other side of the board. And I flip it back. So you'll also see these kind of ghost traces here, these kind of cobweb lines. And this is telling you where each of these pins need to be connected, because it knows from your schematic. So each of these connections is called a net. And you can see they've just labeled them: net J1 pin 14, net J1 pin 13. And the combination of all these nets together, there's a file that KiCad's creating in the background. It's called a rat's nest. And it's basically just like all the nets on your circuit diagram, or circuit design. And we can start kind of like moving these. So sometimes, you can click and drag, but a more secure way to do it is to push the M key, and that identifies it needs to be moved. And you can move parts of it separately. So like I can move just the R2 logo, or I can select multiples and move them together if I really want to. So I'm going to start moving these around in a way that you can see it's telling me where this needs to connect in the circuit. And if I recall, this one was down by J1, and let's see, R1 is up here, R2 is, I think, oh, I'm sorry, I get this backwards. Do I? Yeah, that's by pin 14. Well, let's flip this to the other side. So our connectors, let's assume the connector's on the back side of it. I'm just going to start moving these around in a placement that seems to make sense. Maybe organizes it a bit better. let's rotate this one. So I'm going to zoom in here. And even though a resistor is non-directional, it is kind of directional in your schematic because it needs to know which pin's connecting to what. So I can actually move these. So you can see pink border. Yeah, let's move these, keep it nice and compact. I'm going to intentionally make these a little crooked, and because there's some features here, so I can do things like select all these, and there's alignment tools, so let's see. Yeah, let's align the vertical center. So now they're all nice and aligned. I can do the same thing with this row down here. Now, another thing to keep in mind is the grid. So this drop down up here is the grid spacing of everything. And so the bottom half of this here, you can see 0.01 millimeters up through 5 millimeters are just like a standard, I guess, metric grid. But then above this, it's a grid based on the, I guess it's imperial. But you can see that's 2.54, which is the same spacing we had for this connector. I like to actually go half of that, so 1.27. And what will happen here, you can see moving this around, it's like it's locking into that 1.27 grid. Now when I move these resistors, you can see they're kind of locking into that grid also. When you start mixing through hole and surface mount, that can get a little weird because the surface mount stuff's not really designed for that kind of standard grid spacing. But if you're doing like mostly through hole or trying to line up major through hole components, it makes it really easy. Alright, so you can see now that our sort of like ghost traces here are in a way that they're not a whole lot of overlaps, and they're kind of, everything's near where it needs to connect to. So what I'm going to do now is actually draw out the shape of my PCB. So you can see I mentioned all the layers here. We have the front copper, the back copper. Like those are the areas you're going to be playing around in a lot. You also have front silk screen and back silk screen. So that silk screen again is that yellow layer, and that is what's going to be printed on the board, like in terms of text or lines. And then you have this one down here called edge cuts. And this edge cuts is what defines the shape of your PCB, any holes or cutouts you have in your PCB. I'm going to select edge cuts and then go to draw rectangle, and I'm going to draw the shape of the PCB that I want. So again, there we go. And you can resize this. So you can free draw with a line if you really want to, or curves. There's also a circle tool, a polygon tool. I like to use either the rectangle or the polygon tool instead of drawing lines, because getting these sort of segments to connect to each other when you're drawing a freehand can be infuriatingly difficult sometimes. especially if you need a very specific PCB size or a very specific PCB shape. Right now this is drawn locked to my grid, and there's no real specific sizing here, but when I'm trying to make a board that stacks on top of another board and I want it to be exactly the same size, you can get tiny misalignments in these corners between the vertical and horizontal lines, and it becomes really frustrating to try to get them to connect. But if you use like the polygon tool or the rectangle tool, it just kind of sorts it for you. Another thing you can do is you can select this, right click, and there's the shape modification, and you can add fillets. So let's just say 0.5 millimeter radius, and then what it's going to do is going to curve, put a radius on my corners, and that'll just make my PCB look nicer. It doesn't really, it doesn't, you don't need to do that. I like to do that on my PCBs though. So now that we haven't drawn any traces yet, so none of this stuff is actually connected, but let's click this little 3D render up here and kind of see what our board looks like. And you can see I put the connector on the back side, so that's why it's arranged like that. And you can see how I have all my resistors laid out and where the silk screens appear for those. And because the connector's on the back side, the pin 1 indicator is on the back side of the PCB. So another thing you can do here is you can click this footprint button. So if you wanted to add like a design, I have a logo group. So there's my Twisted Symphony logo, and I could place this on here if I wanted to. But I want this on the back side, let's say. So I'm going to select it and I'm going to push the F key to flip it to the other layer. And you can see it's pink now, which is identifying the back silk screen. So when I click my 3D render, you can see my logo is appearing on the back. Similarly, like if I selected this resistor and I said flip, and then we can see that that's actually placing that resistor on the back side now. So let's flip this back. And I don't need my logo here, but so now we can start doing our traces. So I just saved it again. Now there's an auto routing feature, or free routing. That was one of the plugins that I showed you. Was this free routing plugin? It's kind of neat. So if I click this, that's interesting. So, no, it's trying to show this on my wrong screen. Bear with me for a minute. Well, actually, it completed really fast. So you can see what it did here. It tried to route this. I mean, it succeeded. It drew all my traces for me. This didn't do too bad of a job. I don't know about this decision here. That seems kind of wonky to me. Unnecessary. I'm going to go up here to edit and then go to global deletions, and then what I'm looking for here, traces, tracks and vias, and then delete them all again. I'll use free routing occasionally if there's a section of the board that is like super complicated and it looks like a nightmare for me to do myself. It's just a prototype, so I might just do that. I've grown to prefer to just draw my own traces. So to draw it yourself, select the front or the back, whichever one you want to work on. So I'm going to go front copper here, and then this like blue line here, route single trace. Yeah, as Mitsu said in the chat, free routing is awesome, but definitely double check its work. It in my experience, it produces lots of dead end traces, and it breaks some rules sometimes. You need to kind of check its work and fix it. So I'm gonna just draw this stuff by hand. And you can see, like, I just click on something and it highlights where it needs to go, and you draw it there. Really, really simple, straightforward. Sometimes it kind of makes decisions on its own, like where it wants to route, and sometimes you just gotta play around with it until it goes the place you want it to go. You can sort of adjust these after the fact. Now, like, another thing is, if you look here, like, I drew this one here and it did this little jog down at the bottom, and this one decided to put it in the middle. If I select my select tool, I can actually, like, drag this and try to get it where I want it. Maybe. Like I said, these are some of the quirks. And if you notice, like, I start at the top and go down, it puts the jog in the middle. But if I go from the bottom up, it puts the jog in a different spot. And again, like when drawing the connections on the schematic, you can kind of click midway to lock it in and then continue from there. And just to get these so they're matchy, I'm going to delete these traces. Just select them and push the delete key. Let's try to get these so they're all the same orientation. This guy's a little tall. So there. So now I've hand routed it. You can see it's a little more organized than what the free routing did. It also doesn't have that via to the backside for no reason. Now, one thing here is if we go back to our original. Where's my diagram? If we go back here, you can see that pin 1 is going to 5 volt and pin 14 is going to ground. And we might want those traces to be thicker. So there's a couple ways we could do that. Like, we could literally double click on it and just say, like, hey, I want you to be thicker. Or 0.6. Sure. And it just makes a big chunky trace. And now notice it only increased the size of the specific segment that I selected. And now that'd be super annoying to have to do this through the whole thing. One nice thing is if you have a thick trace like this and then you try to continue from it, as long as there's no other thin traces nearby, it will tend to continue the same thickness for the rest of it. So I'm going to undo that. But what I'm going to do instead is I'm going to show you how to set up a net class. So I'm going to go back to my schematic. So let's say, so in my schematic I have this little power symbol button just below my symbol button. And this allows me to identify things like 5 volts. So I think that's 5 volt, right? Yeah, pin 1, 5 volt, pin 14 is ground. And then I can click this again and can find ground. So now it's gonna that's going to identify that as a 5-volt net, and that's the ground net. And if I go to where is this option? Schematic setup. You can see this net classes thing here. And I can create a new net. So you can see the default is telling me my wire thickness, bus thickness. And let's say ground. And wires thickness 12 mils, so it's double size. And then we're going to create one that is plus 5 volt. Did I do that right? Maybe not. Oh, that's right. I need to set up a pattern. So, what the pattern is it says it identifies the net class based on the name. So when it sees plus 5 volt in the name, it knows it's plus 5 volt net class. And nope, we don't want that. So the net class of ground, the pattern is ground, and net class of 5 volt, the pattern is plus 5 volt. Okay, so now you can actually see it's made these power wires thicker. Because it's identified that as the net class. Now, one thing that you can do is, instead of having to do that every single time, you can import settings from another project. So I'm going to select, let's say this Naomi project of mine, and I'm going to import net classes. You can see it added like a 3.3 volt net class. So that's a nice way to just, like, if you set it up once, you can just import it on your next project and keep that going. So let's go back to our PCB, and I'm going to import again. Not sure if this will import my net classes. We'll find out, I guess. It did. But, so you can see for these power net classes, they're twice the size, 0.4 millimeters. You can change the via size. If you don't specify, it's just going to use the default. But you can see it didn't actually beef up any of my connections because it's not going to modify anything that was already done. So what I'm going to do is I'm going to, well, let's do a global delete again. Tracks and vias, wipe all that out, and now I'm going to redraw. You can see it's a much thicker trace on there for the 5 volt. It doesn't do it for this other one because it's not the 5 volt net. Oops. Push escape to quit out of that if you need to. Man, it really doesn't want to draw that the same way, does it? One other thing when drawing traces, if you notice, is it's making use of a lot of 45 degrees instead of like 90 degree bends. And that's kind of a best practice. from what I understand, 90-degree bends tend to be more prone to damage on the PCB, like cracking or separating. And that's kind of another area where hand routing tends to work better, because I found the auto router loves to put 90-degree bends for some reason. I don't know why these traces don't want to route the same way. Alright, so you can see our 5-volt bus is much thicker now, ground is much thicker now. One other thing that we can do, it's totally unnecessary for this circuit, but let's say you wanted to create a ground plane. So a lot of times I'll do this, like the back side of the board, I'll say like any space that's not occupied by traces, I want to be just a big chunk of ground plating. That's usually good for, it helps with electromagnetic interference, and it helps keep voltages stable. There's a lot of benefits to that. It helps with cooling. So it's not necessary for this because it's such a tiny board and such a simple circuit. But if I wanted to create a plane, I use this filled zones tool. So I'm going to click backside because I want this in the back of my PCB, and I click this filled zones tool. And I can actually, I can draw this like a box. I click and it's going to open this and ask me which net it is. As I mentioned, every one of those connections is a different net, so I'm going to select my ground net. And I'm going to draw a box, and you can draw this bigger than your actual PCB, and it will just automatically shrink to whatever is available. Now you see this little like blue hash around the perimeter there, and that's telling me where my net is. Now, if I go File, Edit, and then Fill All Zones, it's going to create my ground plane. So you can see it's blue because I got the back layer selected, and you can see the shape of it, how it just occupies all the space, it connects to my ground pin, and avoids all the other pins. And I wonder if it shows up on the 3D model. Yeah, it does. So you can see here, this lighter green is the ground plane. It connects to the ground pin. So that just made this big chunk of ground copper on the back. Again, not at all necessary here. And if you need to redo the schematic, or you can always unfill the zones and then refill it if you change around some wiring or things like that. So I think we're kind of done here. We could do other things, like, we could add some additional labels here. So I can click this text box, and what is this called? So this is RE9511. So I can say, well, I don't want it on the copper layer. I'd want this on the front, or let's say back cell screen. RE9511. And I'm gonna let's do front silk screen. We're going to do this again, RE9511, and then we're going to push F to flip it to the back side and put it there. So now we can see, whoops, we got our text on there so we know what it is. We could do that. We could remove these labels, these R1, 2, 3, 4, if we wanted to, and replace it with something else. So like, let's say 4K5. This is on the FFab layer, so like as I mentioned, the FFab doesn't actually come out on the PCB, but we could change that to the front silk screen if we wanted to. And we could take this R1 and we can put that on FFab instead. And now when we make the board, you can see it tells us the value as opposed to the R number. Lots of different things you can do like that. I'll just change this back. So, since we're done, we can do a 3D model. We could see if this will work in our circuit. One of the things I love to do, and I highly recommend when you're at this point, is to print this on paper. So if I click File and Print, you can select which layers you want to print. Obviously edge cuts is probably one of the more important ones. Click Print Preview, and it's going to show me this. So this is what it would print out. And the benefit of doing this is you can print this out on paper, and you can take a pair of scissors and you can cut out the shape. And then if this is mating up with another board, you can see and confirm that everything's going to line up the way you want. So like that that first board I gave you as an example, that multi-kit that I put together, I've probably printed out 4 or 5 instances of that as I was trying to dial in the spacing, because nothing's worse than spending all the time to do this, sending this out to the fab shop, waiting 3 weeks to get it back, only to find out that your spacing was wrong and you have to pay to have it made all over again. Super, super cheap to get this just printed on paper on your desktop printer. Cut it out and then line it up with whatever it's going to connect into, or wherever you plan to use it. Another thing that this is great for is like maybe you selected the wrong pin sizing. Like maybe I selected 2 millimeters instead of 2.54 here. I might not be able to tell that from looking at my PCB layout here, but if I print it out and then I lay it up against the connector I plan to use, it's going to be very obvious immediately that I picked the wrong size and I need to fix it before I send it to fabrication. So yeah, highly recommend print on paper every PCB before you send it to fabrication. I can't tell you how many other people in like the arcade community have been like, oh yeah, I designed this really cool repo board, but it doesn't work because the connector's in the wrong spot. It's such a bummer, especially because you're spending a few $100 to get those made sometimes. Alright, so now what? So now we go to Fabrication Toolkit, and there's some options here. Usually I just leave the default options. One thing I might select is this exclude DNP components from BOM. Now, what is a DNP? DNP means do not populate, and it basically is a way to say, yes, I put this component on the board, but I do not want you to actually put that on the PCB. So if you go to the schematic, and I said, this R13, I don't want this R13. There's these, I just double-clicked on it to open up the properties. And there's these exclude from bill of materials, and there's a do not populate. Don't miss pin 5. Oh, did I miss something in the schematic? So if I click do not populate, you see it X's it out, but it's still in the schematic. We'll save this. We'll go in here. We'll re-import. Update PCB. Oh, you're right, I did miss pin 5. Well, we'll leave pin 5 open for this time being. It's still showing up here, but anyway, do not populate flag would be a way to identify it to the fab shop that you don't want that part added to the board. It's obviously excluding it from the bill of materials is another way to do that. Yeah, one thing I forgot. Just like the schematic, the PCB layout also has a design rules checker. So we can run this, and it automatically fills any zones that you may have forgotten. And now you can see it's giving me a bunch of errors. All right, and the reason it's giving me a bunch of errors is because I have this right angle connector that's hanging off the side of the board. And it's got all this silk screen identified here that's not on the board. So, there's a couple errors here. So, board edge clearance violation, board setup constraint clearance. So this is telling me that the edge of my board is too close to these pins. There's a setting. I'm sure it's in my board setup here. Constraints, there's rules. You can adjust these. I tend to leave it on the default unless there's a very specific thing I'm trying to do. But it's kind of saying, hey, you set up a rule that says you can't have the board that close to a pin, and you've broken that rule. So what I'm going to do, so first I'm going to unfill all zones, and I'm going to, what's going on here? Oh no, KiCad crashed on me. Alright, so I just selected my outline and the filled zone. I'm going to move it down just a click. So all I did is arrow down and then enter to lock that change in. Oh, and it of course missed this edge over here. See what I mean about disconnects? Let's highlight that. Let's make sure we get that highlighted. And that highlighted. I'm gonna move. So I'm holding control as I select these to multi-select. Apparently alright, let's try this again. Select, 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 select. Select, select. Select, select. And select. M for move, down, down again, enter. So now let's run the design rules checker. It's probably going to still come up with errors. Only 2 errors, 15 warnings, so it's giving me an error because there's only 2 spokes connected to ground. I don't really care about that. Silk screen clipped by board edge. So I'm going to right click and say exclude, ignore all silk screen clipped by board edge violations. So that brought my warnings down to 0. And now it has only, let's run this DRC again. So it has unconnected item. So yeah, see, it caught my pin 5. That, chat caught that before the design rules checker did. But this is how you make sure that you get everything. The design rules checker helps with that. We run it again, and we see there's still this one error here for this zone. Only has 2 connections. 2 spokes connected to isolated island, and that's just basically saying like, hey, you have this big filled zone here and you've only got 2 little pins connecting to it, 2 little traces connecting to it, and that's fine. I mean, I don't know if there's anything else we could do about that. As I said, the filled zone is kind of unnecessary for this board, so I'm just going to delete the filled zone, run the design rules checker again, and now we have no errors. No unconnected items. We see we have some ignored tests where we silk screen clipped by board edge. We ignored that because we know and we don't care. Alright, so now we're actually done. And we can click this button for our fabrication toolkit. Before I do that, I think it's giving me grief because of trying to reopen it after it crashed. I'm going to undo this do not populate because I do actually want it populated. So we save that, go back to PCB, re-import to sync them, run the design rules checker again for good measure. Okay, save this. Now we fabrication toolkit, export, and generate. And what this has done is this has created a folder here, and it's given me the zip file. These are my Gerber files, called so because they end in GBR. So this is kind of like the size of the PCB, where all the holes are drilled, the silk screen, where the solder paste goes, where the solder mask goes, where the copper goes, all the stuff they need to actually manufacture the PCB. It also created this BOM file, which is a CSV, and a positions file. And let's just open this with Notepad. So the BOM file is literally, it tells the identifiers, the footprint, how many there are, the value, and then the part numbers that I pulled in from JLB PCB. And then the position file is kind of the same thing, except it tells where the position of everything is on the board. So here the identifiers, whether it's in the bottom board of the board or the top of the board, and then the position on the board, X and Y position. So let's, if we wanted to actually make this board, we can go to JLB PCB, click this instant quote button here, and you can see there's this add Gerber file. So I would take my folder and I just drag and drop this over here. And you can see it's given me a little render of what it thinks the board looks like, so I can look at this and say, hey, that looks right. You can see it's our defaults to a 2-layer PCB. I mean, technically this one I could say it's a single layer maybe if I wanted to. You can see they support all the way up to like 16 layers, even more. Kind of crazy. It automatically calculated the dimensions. By default it says I want 5 of these, but I can have whatever quantity I make. I don't think I need 40,000 of them, but I could make that if I wanted to. Product type. So this is there's a whole bunch of like quality procedures and specifications that if this board is being used in aerospace. As I mentioned, we make a lot of stuff for space use, so we have to use what are called Class 3 PCBs for use on orbit. It's much more expensive, so I recommend just sticking with industrial consumer. Deburring the edge. So if you go to like cheaper fab shops, they'll leave these little spurs on there, and this is just saying that they're going to trim them off. Yeah, JLB PCB is really great. I've used JLB PCB, I've used Osh Park, I've used PCB Way. I've used a few other more expensive US based fab shops for stuff in my professional work. And JLB PCB is really, really hard to beat for the money. Even other cheaper, even PCB Way and like Osh Park, I think they're around the same price, but the quality of JLC PCB tends to be better in my opinion. PCB thickness, 1.6 millimeters is like the standard thickness for PCBs. Obviously, you can get thinner ones or thicker ones if you wanted. You might go with a thinner one if you're trying to do like a quick solder board. Thinner ones might be a great option there. PCB color, you can select the color. I like to go with black on all the stuff that I do. You can see it changes the render to match the color. But you can, there's a few different options here. This is another area where different manufacturers might differ. Osh Park has this really awesome one. It's called like Midnight or something. I'm probably getting that wrong, but it's got this really cool like clear silk screen so you can see all the copper traces, and it just looks really high tech. Unfortunately, not an option here on JLC, but you got your pick of pretty standard colors here if you want. The silk screen color, again, limited options. You could, in theory, here, add additional layers and have a different colored silk screens for multi-silk screen. I've not played around with that. You're kind of on your own if you want to go that route. But it is an option with some manufacturers, not here on JLC. Again, for like material, surface finish, just leave those as defaults. Most of this I just leave as the defaults. This is an interesting one, this mark on PCB. So you could have them add like a 2D barcode if you wanted to. I like to use this order number specify position. And I think there's... Is that right? No. So I'll use this 2D barcode, but then I click number only, and then I can have a prefix. So you could say like, so I put my name there, Twisted 0001, and then this will automatically serialize your PCBs for you. It's pretty cool, and that gives you an actual unique silkscreen number on every one of your boards. So some of the multi-kits I've been doing, I actually have a Cloaks number. So it has a number like this on the board. So every single board I've made has a unique number on it. Just kind of a neat thing you can do to keep track of things. If you click specify position here, so what it's telling you is you need a solid block 2 by 10 millimeters on your board. So on here you would say silk screen and then draw a rectangle, and then you draw a rectangle 2 by 10. So there you go. And you can fill shape. So you put one of these on your board, wherever it needs to go, and JLC PCB will find that, and that's where it will put your serial number. Kind of a neat thing. Let's see, I'll flip this and I'll put it in the back layer. So that's where our serial number could go if we wanted it. So it shows up like that here, but JLC PCB would print your serial number to the specification. But we're not going to do that for this one, so let's say remove mark. And you can see like the price here is super cheap. Like right now we're having 5 of these made. Say we made 10 of them. $5 for the blank PCBs. So this is no parts on it yet. Now, of course, you also have to pay shipping. You can see it's estimating my shipping at $24. And, of course, there's also tariffs because this is made in China. So the tariff's going to be based off of this price, excluding the shipping. And it's like some crazy number right now. I think it's like 80%, something like that, tariff from China. But even with that crazy tariff, I found the JLC PCB is still more cost effective than like US based options. So if I wanted this to be assembled, so like JLC PCB is soldering all my stuff on here, then you use this PCB assembly option. Now, I'm not sure. I know there's a minimum size that they can. This may be too small for them to do assembly. Yeah, the coupons for shipping are really great too. Tooling holes, JLC. Some companies will use fiducials, which are just kind of like a little circular mark in a couple spots on the board in order to know the position of things and line up their machine, their pick and place machine, with the board. JLC uses tooling holes, which are kind of like two little holes that they place in the board. I tend to use this option. They're going to add holes in your board. They're going to add them in a place that's not going to disturb your circuit, and then they'll use that to help align it. Let's see. So their basic assembly option here, their economic option, only allows assembly on one side of the board. So if you have parts on both sides, they're not going to do it for you. I have parts on both sides of this one because I decided to make the through hole connector on the back side. Again, you can select the quantity. So like I'm having 10 boards made, but let's say I only wanted like 3 of them assembled with all the parts. Part selection, this is by customers, means I've already identified all the part numbers, so I'm not going to use JLC PCB's team to find the parts for me. Advanced options here. I mean, most of these are pretty self-explanatory. Bake components, there's a little, all these have like a little question mark here so you can see what it means. I like to say board cleaning. Yes, please clean the boards before you send them to me. Doesn't really add anything to the cost. Other things they can do here, I think there's like a stencil option. Maybe. Oh yeah, stencil. Yeah, you can. Oh, here it is, stencil. So let's say you wanted to assemble this yourself, but it's a surface mount design, and you want like a solder mask stencil. You can have a stencil sent to you to do the soldering yourself instead of using JLC's fabrication. Functional test. I've not played around with this option. I think there's a lot of information you need to give them to do a functional test for you. But yeah, most of the stuff, as I said, I just leave it as the defaults. I like to select board cleaning. So one thing to keep in mind when doing this is you'll want to make sure you know the quantity you want made before you exit that first screen. Because if you say, hey, I only want to make 10 boards and I want to assemble 5 of them, if you change your mind and want to assemble like all 10, you kind of need to go back to the start and start over again, because all of the intermediary steps, which I need to sign in to do, I guess. Oh. Hold on a second. So, yeah, now that I've logged in, it kicked me back to this screen. So PCB assembly, top side, 10 of them, board cleaning, yes. So now we go next. So again, it's going to have you confirm the PCB layout. We go next. Now it's going to ask you to upload your bill of materials and your placement file. So here, BOM. And here's our positions file. So this calls it a CPL file. KiCad calls it a positions file. It's the same thing. And then we process. And this is going to look through my BOM. It's going to find all the part numbers that I specified. You can see those C numbers here. And it's going to say, hey, you know, we have them in stock, and here's the cost. You'll notice that the quantities here are much higher. So I had 6 of these on a board. I'm making 10 boards, so that should be 60, but it's saying 70 here. And you know, this question mark will explain to you that they increase the number on small components like that with the assumption that some of them are going to get lost in production. I mean, if you've ever worked with tiny surface mount components, you know that's true. One nice thing about JLC PCB is they'll like store any extras, so the next time you need them, it pulls it out of your inventory and you save it a little bit. So this all looks good. If there's any issues here, I think it'll throw up flags and it'll like warn you if you try to click through it. And now it's going to do placement. So you can see it's determined the placement of all the components. This one's a little boring. All these certainly look like they're aligned in the right place. You can see that the connector is not included here because it's on the back side of the PCB and they only do single side fabrication. Had we moved it to the front of the PCB, we could have had them do this. If you wanted to, like, you could move these, like you can flip them around if the placement's wrong. I have found that some through-hole components from KiCad appear 90 degrees out of rotation in JLC PCB, and all you have to do is click on it, click the rotate button and fix it, and that's it. I can tell you that if you miss anything here and it's clearly like not lined up in the right spot, JLC PCB will contact you and say, hey, go back and fix it because you're going to have a problem. So they do check over this stuff for you. So once you're done there, it kind of gives you all the pricing and for everything. So you can see the PCB price was $5, but then the assembly is $19 for all 10. You know, $8 setup fee, $1.50 stencil fee, you know, $6 and change for components, you know, 48 cents for assembly, $1.50 for the board cleaning. You know, PCB assembly time is going to be 2 days. Before you can save this to your cart, they're going to ask you to select the description. For arcade stuff, I'm always doing research, education, DIY, entertainment, and then video game, TV, video player. So this is the harmonization code for their shipping. So this is how they identify to customs like what type of thing it is. So 950, 450 is the most common one that I use for arcade and other video game equipment. So I mean that's pretty much it. If I wanted to order this, select this item here. All said and done, including fabrication, assembly. I got a $9 coupon, which is great. The great thing about this coupon is that's against the great thing about this coupon is that will go against the base price here. You know, against the assembly and the PCB fabrication fee, which also in turn reduces the tariff rate because that's what the tariff's calculated against. So this $9, once you include the tariffs, is actually more beneficial than just $9. So yeah, if I wanted to order this, I click secure checkout, checkout, and you can see where it is in the manufacturing process on your orders. So you can see, oh, you know, the PCB fabrication is done and now they're in assembly. And then, you know, you can see the 2 days build time, 1 to 2 days for assembly. So like less than a week, and then this thing's going to get shipped to you. So yeah, that's that's how you do a PCB from something as simple as, hey, I have this schematic I want to duplicate, to having it in your hands so you can actually use it. Looking in the chat, yeah. So Mitsurugi does assembly too. He has a pick and place machine. Definitely looking at him for certain options, because I like using JLC PCB for really quick stuff. But as I'm getting into more complex designs where I have like, oh, I need this really specific. I have this really specific component that JLC PCB doesn't have in their inventory. There's a few things you can do there, but it starts to add complication. Like, this is really easy because I can just say like JLC has all the parts in their inventory. Just make the thing with the parts you have in your inventory. Let's see, what was I going to say? So JLC, let's see if I can find it. There's ways in JLC where you can ship them parts and you can add it to like a personal inventory that you have at their facility. And you can also consign parts. So I think the consign parts is when you ship your own parts to JLC PCB. You can do global sourcing parts. So let's say JLC PCB doesn't have the parts in inventory, but DigiKey does. You can basically say, hey, JLC, buy these parts from DigiKey for me to use. You can also do things like you could put parts on JLC. You could buy parts, send them to JLC PCB, and then other people could buy them from your inventory. Some interesting stuff you can do here. I've not really played around with these options. Typically, if there's a part I need that JLC doesn't have, I'll just exclude it from the fabrication and then, put it on the board myself when I'm done. So yeah, that's how to make a PCB. Hopefully you all thought this was useful, informative. Maybe you learned something, maybe you didn't. If you'd like, I can do another one of these. Maybe talk about some more complex topics or interesting designs. I'll release the project files for people to look at if they want. Not a problem at all. Let's see if there's anything else super important to cover. I didn't talk about the flags. So you know what? I'm gonna let's do another quick and dirty board design. So let's close out of that. We'll close out of you. Close out of you. And we're going to close this project. And we're going to say new project. And I'm going to say simple multi. Right? Simple multi. So I'm gonna show you how to make the world's most simple multi-kit for an arcade board, or anything that uses an EEPROM. So I have these socket headers that I created, and these are you can see the footprint here looks like an EEPROM, but this is really for the pins that go on the bottom of the board to plug into an EEPROM socket on, let's say, a normal PCB. Now, I have a 27C080 socket header here, but I'll place that there, and we're gonna let's do a 27C160. So that's a 16-bit, and let's we'll throw a rotary switch in here, and then we need like some resistors. Okay. Is this everything I need? I think so. So we have a socket header. So this is gonna plug down into our donor PCB and like our motherboard. And then this is a socket for a 27C160 EEPROM. So I think anyone that's in the arcade enthusiast community probably understands what EEPROMs are. If you don't, it's like it just stores code. So 27C080 is 8-bit. And you have these address lines here that are identifying where in the stored data it's looking for information, and then these D0 through D7 are the 8 bits that it outputs. So if these A0 through A19 are all zeros, then this output is going to show you the data that exists at address 0. And then if you have A0 turns to a 1 and the rest are zeros, then this data is going to change to whatever's in position 1, and so on and so forth. So you have a binary input selector and then a binary data output. And then these chip enable and output enable, both of these need to be activated in order to output data. Now, let's see what we'll do here is, because this is a 080 is a 8 megabit of data, and a 160 is 16 megabit of data. This one is essentially twice the size of this one. So we can bank switch. And we're going to assume that this is actually a 27C040. And so that's half the size. So that makes this one 4 times the size of this one. So the difference between a 080 and a 040 is this A19 pin. A 040 doesn't have it. So what I'm going to do is this little X connector here, I'm going to take that, I'm going to stick it on A19. And that means that that pin is not connected to anything. We do that because the design rules checker is going to, if it doesn't see that, it's going to throw an error and say, hey, you forgot to connect pin 19. And we're going to do some simple stuff here. So I'm going to add a ground. Alright, ground to the ground pin. And I'm going to copy that and paste it to the ground pins here. And then again, I'm going to take this, I'm going to take 5 volts, not negative 5 volts, plus 5 volts. And I'm going to place that up here. And again, I'm going to copy and paste. And now I'm going to connect these together instead of drawing lines, because that could get super tedious and super confusing to look at. I'm going to use labels. So we have net labels here. There's a couple different ways you can do this. So there's regular net labels, and then there's global net labels, and then there are hierarchical labels. I'm not going to get into hierarchical labels. That's kind of like a super advanced feature. If you have a schematic that takes multiple pages, you can kind of treat the pages like they're components, and it's a super powerful thing, but it is super complicated. Maybe for another lesson we'll go over those. But for now, you can either use regular net labels or global net labels for a single page schematic. They're equivalent, but I'll just use regular net labels for now. And I'm just going to say A0. And I'm going to rotate it, oops, so I can stick it on the A0 pin, and then click again and say A1, rotate, rotate, A2, and I keep going through this. There is a bus feature that you can use for this. I tend to I've not really used that for some of this multi stuff that I've done, because you're kind of slicing and dicing the buses when you're doing this kind of work, so it doesn't make sense to use the bus labeling feature that they have. A little tedious here, but it'll make sense in a moment. Alright, so I've got addresses A0 through A18. Kind of just look over these, make sure I didn't misnumber anything. And now I can kind of take this whole row and copy it and paste it over here. And the nice thing there is I don't have to worry about mistyping it. Now you notice actually, this is incorrect. So these actually, because the 27C 160 is both 8-bit and 16-bit, the numbering here is offset by 1 when it's in 8-bit mode. And because we're going to use this in 8-bit mode, it goes like this, with A0 over here on A -1. You notice it says D15 or A -1. And then you have this byte VPP pin. So when this pin is low, it's in 8-bit mode, and when it's high, it's in 16-bit mode. So we're going to use this in 8-bit mode. So we're going to actually take a ground, and we're going to tie that pin to ground to make it low. So now we have A18 and A19 that aren't connected to anything because they're not being used by this socket here. Let's also do our D pins. So we're going to place some more labels. D0. Again, I'm going to copy these and put them over here. And because this is an 8-bit mode, not 16-bit mode, data pins 8 through 15 are not used. As a matter of fact, 15 gets repurposed as the lowest address bit. So now we also have chip enable and output enable. So again, we're going to create some labels for that. So we have CE and OE. And these labels can really be anything that you want them to be. As long as they're consistent. So now we have this rotary selector, and we're going to use the rotary selector to do the higher address lines. So we'll call it cell 1 and cell 2. Actually, so I just copied those. I'm going to move that here and move that here. And honestly, these probably shouldn't be connected directly to the selector. So what we're going to do is, because there's only 2 selection lines, we don't need these higher level ones here. we're going to tie the common pins of the selector to 5 volt. And then we have this resistor here. Let's say the value is 4.7K. Oh yeah, we need a footprint, don't we? Let's go with the 603 hand solder. And we need at least 2 of these because we have 2 selector pins. Let's move this. Again, M key for move. And here we'll draw some lines because it doesn't really make, it's more effective and efficient to draw the traces out than it is to do labels on this section. And we're going to attach this selector label to these. That'll have two effects. One, it'll make this part of the selector 1 network, and it's also connecting this to, over here. Now we need grounds. So I'm just copying these over. Okay, so this is essentially a multi-kit, a bank selector multi-kit. So what we have here is we have a 27C040. If the board that you had originally used a 27C040 4 megabit chip, EEPROM chip, this PCB will have a 27C160 socket, so it can store 4 times as much code, and then you can select what code bank it's using, which of the 4, using this switch. The reason we're using these resistors here is that normally, so if you think of this like a dip switch, when the dip switch is off, the pin, the select 1 or select 2, is connected to ground through the resistor, so it's going to show low or a 0 value. And then when you turn on the dip switch, it's going to drive these high by connecting to the 5 volt, and it prevents a short. That's why you have the resistors here, because you can't have one end connected to ground and the other connected to 5 volt, or you create a short and you'll burn up traces. But the resistor takes on that protection, and it allows that pin to go high when you make that connection. So this rotary selector is really just a fancy dip switch. So we're basically able to toggle address 8 and address 9 in one of 4 combinations, either off-off, on-off, off-on, or on-on, to select one of the 4 banks here. So let's run our design rules checker. There's 2 errors on the power pins. I'd expect those because I'm not specifying the power source. I could modify this a bit to say, hey, you're getting your power from these pins on the socket header, but I'm not going to bother. But you can see, like, because we use these labels, instead of drawing traces, it makes it a lot easier to read and understand, and a lot cleaner to look at, while still having the same sort of functionality as drawing all those lines. So let's import this. And we'll drop it here. And I mean, this is not a bad layout already. One thing we need to do is, because this is a socket header and not a chip, we need to flip it to make sure it's on the other side of the PCB. Also notice, like, I can kind of free drop this wherever I want, so I'm going to change my grid spacing to 2.54. So now when I move this, it'll help me keep these super in line. You can see you know what else? This footprint is not the footprint I want to use. So let's go back. I did make a custom footprint for this, and I don't think I've associated it with a rotary switch yet. So we'll re-import. There we go. Interesting. So you can see that these surface mount don't exactly line up with stuff. That's okay. Let's do edge cuts, and we'll draw a box around this. And I'll right click on it and go to shape modification for fillets, 1 millimeter radius. And you know what we'll do? We'll undo that. I'm gonna expand this a bit. So that we can add some through holes. That's way too big, so I'm gonna shrink my go 1 millimeter spacing here. So I'm gonna copy this. So if you wanted some through holes in your PCB, that's a way you could do it. And if you really want to play around with positions, you can adjust. You can specify the radius and the X and Y positions, and really dial this in. Right-clicking, there's all kinds of positioning tools to dial in the position exactly where you want it. Shape modification, fillet, 1 millimeter. And now we could draw our traces. So, well, for the sake of speed, I'm just going to auto route. This is the auto router working. Not the prettiest auto route, but hey, it's done. And you know what else I realized is I didn't pull in my my nets for larger 5-volt ground traces. So let's global delete tracks and vias, board setup. Actually, schematic setup, net classes, import net classes from, we'll use that Naomi board again. Update from the schematic, and board settings, net classes, good, those are there. So now we'll do free routing again. So now we have thicker traces for a 5-volt, and this one could benefit more from a ground plane. So we'll go back copper, filled zones, ground, and we'll draw our box. And again, this can be larger than your PCB. And we'll click Design Rules Checker. So what do we have for errors here? We have warning for a silk, so no disconnected items, that's good. Silk screen overlap, oh yeah, so my R1 is overlapping. Thermal release, again it's complaining about some of my ground pads not connecting to the filled zone very well. So let's just move this silk screen down here so there's no overlap. Run this again. Silk screen clipped by board edge. Aha. Again, let's move this label, move it right in the middle. So it's just giving me grief about some of the ground pads, but that's not a big deal. So now, oh, I just realized I used the wrong component. So this you can see I selected a socket header, and that was supposed to be a socket, not a socket header. So there's a couple ways to fix this. I could go to Properties, and I could update the symbol or edit the symbol, change the symbol. Let's do that. I'm not going to do that. I'm going to delete this. You can see all the labels and everything stayed there. And I'm going to pull in the correct item, which is ROMs 160. And it is the exact same size because I drew it to be the exact same size. Now this is probably going to give me some grief here, but we'll see what happens. Yeah. So it left the old socket header, but let's get my grid correct. Move this, and it should line up exactly the same. Oh no. It doesn't like it. So we'll what are we going to do? We're going to global delete, tracks and vias. Okay, and I'm going to update again. I'm going to remove footprint fields not found in symbols. So that's going to ensure that's removed everything that I deleted from the schematic. And now we're going to unfill the zones, and we're going to free route again. And design rules checker. Okay, that's much nicer. Segment on edge cuts. Okay, label needs to be moved again, so I'll move that over here. And then the ground zone thing again. Unconnected items. Huh. It looks like free routing forgot to connect some of my grounds, so we'll do that manually. Oh. Bottom. Go. This ground's kind of all alone. Let's go top. Let's see, are there any other grounds disconnected? So again, the only grief it's giving me is because this ground pad is connected to a ground plane with nothing on there, which is fine. Okay. So, let's see how this looks. Much better. So, here we have the world's most simple multi. If you had a 27C040 EEPROM, you could replace it with this board, and this board would have a 27C160 chip in it, and then you could use the switch here to bank switch between 4 different ROMs. And expanding this up into the program ROMs and the sound ROMs and the graphics ROMs all controlled with the same switch is really the basis for most multi-kits on arcade hardware. Technically, you could do this on like console cartridges as well, bank switch the EEPROM there. So if you had a video game home console that used a 27C040 EEPROM, this could have a 4-in-1 multi-cart with a little switch here. So yeah, how long did that take us? Like 20 minutes to throw together a really, really simple multi. And doing a more complex multi-kit is really just this with more. Certainly if you start getting into other stuff like, you want to change security features, or maybe there's some programmable logic that you need to switch between it, you start adding a lot more complexity to it. But yeah, this is the basis for a lot of it. I'd say, if you want to get into PCB design, find a project, find something that you can kind of in your head understand how it needs to come together, and then just start doing it in KiCad. Ask questions on forums, use Google search, ask ChatGPT, find tutorial videos online as to like how to do certain things. The information's out there, but the best thing to do is to have a project and just kind of start. Hopefully I've given you in this stream what you need to get started here, and when you run into things you don't know how to do, figure them out as you come along, and then just keep going until you get your project done. But having that project in mind, having an idea of what you want the end goal to be, is really important for learning, I think, because you're going to get a lot more out of it than if you're just following some tutorial that ends with a thing that you don't use or care about. And then once you've done one, challenge yourself to do something a little more complicated, and then once you've done that, challenge yourself to do something a little more complicated, and keep going, and that's how you learn and build skills. All right. I thought this was fun. If there's other topics or similar things, maybe people want to know about SolidWorks. I know a lot about SolidWorks for 3D modeling. If people want to know more advanced KiCad features, people want to know about other stuff, let me know, and we'll see about doing another stream. But thanks all. This was fun.